Start recording. So recorder is up. And today we're going to start with a new topic, which is introduction to arrays. I cannot talk about exam one yet, okay, because there are people who, at least one person is still out sick, okay, and I'm waiting for the doctor's note from that person as well, okay, before that person can take a makeup of the exam. But I still cannot talk about the exam as a result of this. Yes, go ahead. Not yet. Yep, I'm a little behind in terms of grading, but I did give you guys the solution of the assignments. Yep, so that's important. So what we'll do today is we are getting into arrays. Okay, so this is a new module. Okay, I just finished it this morning, so I do apologize that I cannot, finish it early enough to give you guys a chance to read it before class. So this is the module. It does have prerequisites of 12, 13, and 16. So that means, if you want to make sure that you have all the background material to understand this particular module, you might want to go back and revisit module 12, 13, and 16. And 12 is, let's see, variables. Okay, thank you. And then 13 is conditionals. Okay, and then 16 is loops. Okay, so those are the three kind of prerequisite requirements or prerequisite modules to understand arrays. All right, so now we can get started with the objective of this particular module. We are here to introduce the concept of arrays as well as two simple algorithms that involve arrays. Okay, so arrays are really super important because without arrays, a lot of algorithms cannot even exist. Okay, so this is a construct in programming that is essential for many algorithms, regardless of the programming language. So in this class, we focus more on the concept rather than the language itself. But it is still kind of important to choose one particular programming language, and I'm choosing to use C++ as the syntax for this class. So the first thing we do is we revisit two algorithms that we already know. This is an algorithm to find the maximum of two variables and store the maximum in variable m. If a is greater than or equal to b, m, which is the variable supposed to store the maximum, has to be a, otherwise m equals to b. So we have already visited this particular algorithm. And if you say, what if we have three variables? Okay, what if we have a, b, and c, and I want to find the maximum of a, b, and c and store that maximum into variable m. Now that algorithm also has been introduced, and it looks like this. Okay, and the indentation is actually correct, to reflect the nesting of the structure. So this one goes, if A is greater than or equal to B, and A is greater than or equal to C, then A is the maximum, and as a result, M gets A. Otherwise, we also check whether B is greater than or equal to A and B is greater than or equal to C. If that is true, if the conjunction is true, then B is the maximum, and as a result, we store B to variable M. If both of these conditions fail, then variable C has to be the maximum. And so in that case, we store C, into M, which is the variable supposedly to store the maximum. So do we have any questions about the algorithms? One to find the maximum of two variables, and then the other one to find the maximum of three variables. Do we have any questions about those two? Hmm? Yes. So that's what this algorithm is about, is to find the maximum of A, B, and C, and then store that maximum in variable M. Okay, all right. Because we did a homework assignment on this. Okay, we did a homework assignment on this, and I even drew the flow chart for this one. So hopefully this is not you know um, a big question at this point. Okay. So the next question is, what if you need to find the maximum out of 20, 200, or 2,000 or 2 million values? They go like, well, we can use this approach, but that program is going to be kind of long and kind of tedious. And, well, it's not super complicated, but it's just tedious, okay? And we don't want to do it that way, Okay, yeah, this is great. If it is up to three, the four variables is already a little bit kind of cumbersome. Okay, so we want to find a way to handle more values without making the algorithm any more complicated. So I'm proposing an algorithm that looks like this. And yes, you're correct. We have not even talked about arrays yet. So you may not understand what this code is about. The one thing that I want to tell you about this code is it will work regardless of whether we have 20 values, two values, 2,000 values, or 2 billion values to find the maximum out of. It is the same code. Okay, all the only thing that's going to change is n. So n is the number of items or number of values, but we only have to change, what the value of n in order for this algorithm to work on different numbers of values. Isn't that great? Okay, it doesn't look any more complicated than the one before, and yet it is scalable. So this is a very important term, whether an algorithm can scale up or not. Can anyone tell me what does that term mean? When I say scaling up, what? Hmm. Okay. Okay, that's not a bad explanation. Anyone else want to? Yep, go ahead. Not exactly. Okay, so let's go. Ask Chat GPT what does the phrase scaling up mean? Okay, so I do encourage people to use Chat GPT when it is a good opportunity to use it. So I need to ask it, what does scaling up mean in the context of algorithms? So, this is not just any context, it is in the specific context of algorithms. So we'll see what the answer is. Scaling up refers to how an algorithm performs as the input sizes increase. Key aspects of scaling up: time complexity, how does the how much time it takes for the algorithm to complete increases as the problem size increases, space complexity, optimization, and so on. So in this case, we are only concerned about the complexity of the algorithm itself. In other words, we want to use something that looks like this, which is a very fairly small number of lines, to work when we have 20, 200, 2,000, 20,000, 2,000,000, values where we need to find the maximum out of. So scaling up means, if an algorithm scales up, it means, it is not going to be super complex or in some cases time consuming as the size of the problem increases. So is that working out with you guys? What scaling up means? Okay. The number of lines in this case of the algorithm stays the same, even though the problem itself is a lot bigger. The number of lines involved remains exactly the same. Okay, and arrays is what allows us to specify a lot of algorithms that are very scalable. Okay, so that's why arrays is a very important topic. So the next section talks about what exactly is an array. So an array can be seen as one variable, and it can also be seen as its components. However, it is actually an array is the composite of many elements. In C and C++, arrays has several attributes. So the first one is all elements in an array must have the same type. Now, this doesn't really make a whole lot of sense to us because I haven't really talked about types. Okay, so types refer to what you can store in a variable. Yeah, data type. So there are two main data types. You have strings, which is basically text, like the name of a person, like the street name, okay, and so on. And then the other one would be numerical values, okay, such as your year of birth and so on. Those are numerical values. So we have mainly two types. But in C and C++, every element in an array must have the same type. In other words, you cannot have one element in an array being the name of a person, and then the next one refers to a number, a numerical value, and so on. Okay, they can all be numbers, or they all have to be text. They cannot, you cannot mix and match. Because there are multiple items in an array, each item or each element is identified by its own index number. Okay, so that means every element in an array has an associated index, which is no more than a natural number that serves as an identifier for that particular item in the array. The index of the first item or the first element is always 0 in C++. Okay, the indexes of elements must be contiguous, which means we cannot skip numbers. You have element 0, element 1, element 2, element 3, and so on, but you cannot skip numbers. You cannot go from 0, then to 2, then to 4, and so on. They must be contiguous as natural numbers. So far, do we have any questions? I know this sounds awfully vague, but by the time we get to an algorithm and look at the trace, hopefully it is not going to be as vague anymore. Yes. Yes, it is also seen as a list. So depending on the programming language, in Python, typically people call an array a list. So they can be used somewhat interchangeably, but they are really not exactly the same concept. Yeah, so in the case of an array, you can get to any element in the array at with constant time. So that means if you have an array of, let's say, 1 million items, okay, you can get to the last item just as quickly as getting to the first item. On the other hand, strictly speaking, if it is a list, then it would take longer to get to the last item as opposed to the first item. Okay, so that depends on how strictly do you want to kind of call an array a list. But in the context of C++, an array is not called a list. They are not used interchangeably. So do we have any questions about this, which is the naming of, array as opposed to um, a list? Yep. It does not quote unquote change. So let's just say that we have 5 elements. Okay, so everybody on this row is an element in an array. So the thing about an array is every item, so they belong to the same array. Okay, there are 5 elements in this particular array. But I have to be, sometimes I refer to the entire array as one thing. Other times I need to say, oh, I don't want the entire array. I just want one particular item in the array. So that means each item in the array needs to be identified somehow. And the identifier is really just a natural number which starts from 0. So that means element 0 is one particular element in the array, element 1, element 2, 3, and 4. So that's how we identify individual items inside an array, because an array is a composite of multiple items. So does that, yep, okay. All right. So the number of elements in an array in C++ must be quote unquote given. Okay, so this is a really important concept. In most other programming languages like Java or Python, you can query, you can ask an array and ask, oh, how many items are in this array? Okay, it works in all of those other programming languages. But in C++, it does not work. There's no easy way to ask an array how many items are in the array. So that means from the consideration of algorithms, most of the time, if not all, you have to be told the number of items in an array. You cannot query an array and ask how many items do you have, because the array actually does not know. And I know this sounds really vague, okay, but that is how it goes in C++, okay? Um, so for now, we just say that every time we deal with an array, you probably need to ask the question, how many items are in the array? How do we know the number of items in an array? All right. So the last item in the array has an index that is double quote, the number of items in the array minus one. And the reason why that is the case is because we count from zero. Just like the example, we have an array of five elements, okay, looking at people on the second row. So since you are element zero, right? You're element one, two, three, and you being the last element of an array of five, you have an index of four and not five. That's because we counted from zero. Does that make sense? Okay. Now, I know it doesn't sound very natural to count from zero, but you will realize that in all, almost all programming languages, they always count from zero. Okay, and the reason why we count from zero is not going to be clear until you take CISP 310, not even 360. They won't tell you why we count from zero in CISP 360, but in CISP 310, which is computer architecture and organization, or something like that, then we'll start to understand, oh, okay, so counting from zero actually makes a lot of sense. So for the time being, between this class and CISP 360, you just have to constantly remind yourself that you have to count from zero. Okay. All right, the last element in an array has, okay, we just finished that one. An element with index I in array A is represented as A, and then we use the brackets to enclose the index of the item. Okay, so that's just a syntax. Okay, I know everything is kind of abstract right now. Okay, so we're going to look into an algorithm. So we'll look at this particular algorithm here, and then we'll trace it. All right, so this is the algorithm. Let me kind of scroll up a little bit and then magnify a little bit here. Okay, there we go. All right. So the only job of this particular algorithm is to initialize, which means we give each item in the array a specific value of zero. Okay. In other words, I'm given an array. I just want to make sure every element in the array ends up with a value of zero. Does everybody understand what the algorithm is supposed to do? Okay, we good? Okay. So variable I in this particular algorithm, I call that an indexing variable or the index of the algorithm. Yes, go ahead. 0, 1, 2, 3. Yep. Yeah, I is used to identify which element in the array we want to deal with. Yep. It helps to designate. It helps to identify or designate which element in the array do we want to work with. That's what indexing is for. But otherwise, I is just a variable. It really is no different from any variable that we have talked about up to this point. You can use it, you can refer to its value, you can initialize it, you can change it. You can see how line 1 initializes I to 0, and then I4 increments I. So I goes from 0 to 1, 1 to 2, and so on. And then we use I in on line 2 for comparison. So it acts just like any variable because it is just a general variable. So that's line 1. Line 2 says as long as I is less than n, we stay in the loop. Okay. In other words, one thing you can do to help you remember what while means is it is the same thing as long as. Okay. So this means as long as I is less than n, we are going to keep performing line 3 and line 4. Is that okay so far? Okay. So the most important line of this entire algorithm is line 3. So line 3 is, it is an assignment operation or assignment statement because we can see that there's an single equal sign. It has a right-hand side, which is a constant of 0. What makes it kind of interesting is the left-hand side. So the left-hand side is not really just a single variable. It is telling us, oh, we are going to make changes to item I of array A. Is that okay? So in C and C++, okay, you cannot make changes to every element in an array with one single statement. You have to work with each element of the array individually. And using the loop, we now have the mechanism to go through the entire array and then initialize each item individually. Do we have any questions about the algorithm? Nope. Okay. All right. Yes, go ahead. It's a method of doing things. That's part of the title of this class. So what is the title of this class? It's algorithm design and problem solving. Okay. Yep. Okay. So an algorithm is it means a method of doing something. You can also just look it up too. You can go to ChatGPT again, explain the word algorithm. Okay. An algorithm is a finite, well-defined sequence of steps or instructions designed to solve a problem or perform a computation. That's pretty much what algorithm means. It's just a very fancy word to say method. Okay. Yep. All right. Moving on. Instructions. Yep. Well, they're not rules. They are instructions. They basically tell the computer what to do. Yep. So the analysis of this algorithm is performed here. Okay, so you can read this, on your own as well. But they basically just we say the same thing that I said a little bit earlier. Um, the condition of I is less than n is important. In other words, we only want I to be within the range of the indexes when we are staying in the loop. As soon as I is n, we need to exit the loop because n is not an is not a valid index into the array because it is already past the end of the array. The last item in this case has an index of n minus 1. All right. So as as I know this is this sounds really kind of abstract and kind of difficult to understand maybe at this point. So what I'll do is I am going to keep the algorithm shown in this picture here, and then we'll scroll down to a trace of the algorithm. So hopefully this will give you a better idea of how it works. Okay. So the way we trace algorithms is kind of the same thing, like before, except this time, instead of having one single column for the entire array A, we have one column for each element in array A. So A bracket 0 is its own column because it can store its own value. The value that we store in the first element, which is element 0 of A, is independent to the value that we store in the second element of A, which is also independent to the value that we store in the third element, which is element 2 of the same array. So is that understood? There are multiple items in an array, but the items are independent from each other. Is that okay? All right. Yep. You have to be told. So that's why n starts with a value of 3. It's on the precondition line because you have to be told that it has 3 items because you cannot query an array how many items do you have. In C++, that's not possible. Yep. No, I is independent from the array, and that's why I has its own column. So you can see that I is just a general variable. It has its own column. In fact, other than n, everybody starts with an unknown value. All right? But the most important part is to look at an array and understand that, oh, it is not a single column. Okay? An array with 3 elements in it would take up 3 columns because each item in the array can store its own value independent to everything else in the array or in the entire program. Yep. It is just you have to be told what n is. So n in this case has to be consistent with the number of items in array A. You can see how array A has element 0, element 1, and element 2. So that's why n, which is the number of items in the array, it has to be 3. Now, but that begs a second question, which is what if n is not consistent with the number of items in the array? So if n is too big, we can end up with a problem. In other words, we can access memory that you're not supposed to. It's very bad. It's not just bad. This is like beyond bad. This is one of the main reasons why we have stack overflow and other types of vulnerabilities when it comes to programs. Okay. So as a side topic, okay, I think in your future you might want to look into Rust as a programming language. Yeah, so Rust as a programming language has all the good stuff about C++, but with none of the drawback of C++. And one of the drawback of C++ is you can access an array out of bound, which means you're trying to access an element in an array that does not exist. You basically just either reading or overwriting certain locations of memory that you're not supposed to. C++ programs can do that just like that, okay? But in Rust, it is much more protected, and you cannot easily, or I don't think it is even possible in Rust. So that means, in your spare time, okay, after this class, and you still decide you still want to continue to pursue computer science or software engineering, you might want to spend some time to learn Rust in addition to C++. Rust is not going to be helpful in a university or a college. In other words, none of the classes taught here or at a normal 4-year university would use Rust. Okay, that's just truth. Okay, unfortunately, that is the truth. But it is going to be very helpful when you need to find a job. Yes, it is fairly new. I would say it's probably a couple of years old, so maybe 4 to 5 years old. Google came up with Rust, okay, to basically remedy a lot of problems that are associated with C++ as a programming language. So it's a more modern programming language. It fixes a lot of the problems that we already know exists in C++, but it is still not widely accepted in universities, as a programming language that they use for teaching purposes. But in industry, people are already shifting to start to use Rust. It's going to take some time before it is widely used in industry, but because you guys are about 4 years from graduation from a 4-year university, so starting now, understanding your learning Rust is going to be helpful to you. Yep. hmm Okay. So I know the answer, but I want to show you how to use ChatGPT again as a tool. Okay, because Sam Altman said, okay, the most important skill set, for your generation, for your career, is not to know everything, but to know what questions to ask. Mm, how to learn, but also to know what question to ask. How do you formulate your question? So in this case, we want to formulate a question like, you know, um, comparing, okay, C++ to Rust. What are some of the advantages of Rust? So that will give you, I mean, I'm sure it will give you the correct answer in this case. Memory safety without a garbage collector. Now, obviously, um, we are even at a 4-year university. Okay, the concept of a garbage collector is fairly advanced. Okay, but I can just tell you that garbage collection is a concept that can slow things down in an unexpected way. Okay, things are not predictable when you have a garbage collector. But you also want memory safety, which is kind of what we just talked about. Okay, if you try to access an element that does not exist in an array in C++, the programming language just let you do it. Okay, even though it's a terrible, terrible idea, but the programming language does not know where the boundary of the array is, so it cannot enforce any rules. Rust can enforce memory safety, but without incurring the cost associated with garbage collection. So it has the advantage of both Java and C++, but without the drawback of either one. Concurrency without data races. So it basically has language level feature that allows you to write programs that specify multiple threads. Okay, in other words, portions of your program are running at the same time, quote unquote, concurrently. With a normal programming language like C++, you have to go through a lot of work to make sure that one thread does not step on the toe of another thread. Because when that happens, when that kind of interaction happens, the bug or the symptom of the bugs is very difficult to observe because when you have no telling when it's going to happen, and every time it happens, the symptom can appear entirely differently. Okay, so concurrency without data races, make sure that those programs are easier to debug. So basically, this is a long list of items of why Rust is a much better programming language. But to adapt a new programming language, even at a college level, it's difficult. Okay, because you have to change the textbook. All the professors have to learn the new programming language, learn all the tools associated with the new programming language, etc., etc. Um, we are fairly mobile, at ARC, but where do you guys, what do you plan to do once you get your associate degree, from ARC? Transfer, exactly. So when you transfer to UCs and CSUs, if they are not ready to teach their classes in Rust, then you're still stuck with C++ or Java. Okay, so there's a certain momentum associated with the entire education system, and not just us as a community college, but also it extends to the four-year university. So that means, it is not very likely that we are going to see a change in terms of, how um, which programming language ends up being used at a four-year university. If you're lucky, you might get into a UC or a CSU that teaches Rust, but more likely than not, you're going to continue with C++ or Java at a four-year university. All right. So getting back to this algorithm, getting back to the trace. Okay. So on line one of the algorithm, we have an assignment statement. The right-hand side is a zero, which means this is the value that we want to store. The left-hand side is I, which is identifying which column we want to store the value to. And as a result, in the trace on line one, I is changed from whatever it was before, which is unknown, to a zero. Okay, so are we good with line one in the trace? Okay, line two is a while loop. Okay, the while loop says the condition of the while loop is I is less than n. So we have to evaluate that particular condition and say, okay, but is it true or false? So in order to evaluate line two or the condition of line two, you look up the column with the value of I, and at that time, I has a value of 0. So the question is really saying, okay, is 0 less than n? What is n? You look up the value of n. N is a constant. It never changes, right? So it's always 3. Is 0 less than 3? The answer is it is true that 0 is less than 3. When the condition of a while loop is true, what do we do? You continue with the loop, right? You do not exit the loop. So that means we continue execution on line three. So line three, once again, is the magical part of this algorithm because the right-hand side of line three is simple. It is just 0. It's just a constant, okay? Not a problem. The left-hand side, on the other hand, is a little bit interesting. Because we are using A and then we use a square bracket notation, which means I need to get to one of the items of array A. Is that okay? So when you see the name of an array followed by square brackets, that means I need to get to one of the items of the array. But which item do we want to get to? So inside the square bracket is an expression. Okay, in this case, we have a very simple expression which consists of just I by itself. But nonetheless, it has to be an expression that gives you a natural number. So in this case, what is the value of the expression I? It's 0 because I itself has a value of 0 right at that point. So that means A bracket 0 becomes A bracket, excuse me, A bracket I becomes A bracket 0 because I is 0. Okay, so now we go like, oh, I know where to find it. A bracket 0 is this particular column here. So that's why that column is now getting the value specified on the right hand side, and it is now changed to 0. So we are focusing on just this row here. Do we have any questions about the row the first time on line 3 that we change the value of an element of array A? Do we have any questions about that line? Okay, so you go like, okay, then what do we do? Well, the next line, which is line 4, is I gets I plus 1. Since I is currently 0, 0 plus 1 is 1, and then we store that value of 1 back into I, and as a result, I is now updated to a value of 1. So this part is not should not be surprising, okay, because we have done homework assignments on loops and how we update values of variables in a loop. So this is a fairly simple case of how we update a variable in a loop by incrementing it. And then what do we do? Well, since line 4 is the last thing in the block statement, that is the body of the loop, that means we are done with the body of the loop. So what do? We have to go back, okay? So we go back to line 2 and reevaluate the condition of this loop, which is I is less than n. So that's why we go back to line 2 over here, okay? Let me use the mouse pointer. Okay, so that's why we go from line 4 back to line 2 and reevaluate the condition of the loop, which is, oh, I is less than n. Is it still true? Well, let's check it out. What is the value of I at this point? The value of I is now 1. The value of n does not change. It is still a 3. 1 is less than 3 is still true. So that's why we come to the conclusion that I is less than n is true. And then we both go back to line 3. And this is why indexing is so useful, because line 3 has not changed. Line 3 is still a bracket I equals to 0. But this time, because I itself, okay, variable I itself has changed from 0 to 1, that's why when we refer to a bracket I, it is no longer referring to a bracket 0. Instead, it is now referring to a bracket 1, and a bracket 1 is the one that is getting a value of 0 this time. So does everybody kind of get the idea of why indexing is useful? Because it allows you to specify any expression between the brackets, okay, in a loop, and as long as that expression uses a variable that is changing for every iteration of the loop, you can now address or you can now specify a different item in the array for different iterations of exactly the same loop. That is the power of using an array, because you can use an expression to specify which item within the array do I want to access. Now, in this case, the expression is just the variable I itself. It doesn't have to be that simple. It can be very complicated. It can be very simple. But the point is, it gives you the flexibility to use an expression to express which item in the array do we need to access. Yes, that is correct. We are not trying to find the maximum in this case. We are just initializing the array so that each one starts with a value of 0. Mhm. All right, so after line 3, We go to line 4, okay, and this time on line 4, we are incrementing the value of I from 1 to 2, and then we get back to line 2, which is re-evaluating the condition. I is less than n, is it true or is it false? But at this point, I has a value of 2, 2 is less than 3 is true, so that's why we have to go to line 3. On line 3, this time, we are putting a 0 into A bracket 2, because this time around, I, okay, let me try to zoom at the right level. Okay, I might need to go up one level like this. So at this time, okay, when we look at this row here, I has a value of 2. So when we evaluate A bracket I, it is saying A bracket 2. And that's why A bracket 2, which is this particular column here, it is now updated to a 0. Yep, go ahead. Yes, if I did not change, then we would be reinitializing the same thing, and we would not be able to exit the loop. Because as long as I remains as a value of 0, then I is less than n is always going to be true, which means we cannot get out of the loop. So we'll be putting the same value of 0 onto the same column, which is A bracket 0. Just we keep doing the same thing without any chances of exiting the loop. Is that okay? All right. So after line 3, we get to line 4. We finally increment I from a value of 2 to 3. We still have to go back to line 2 to reevaluate the condition of line 2, which is I is less than n. But because I is 3, n is also 3, I is less than n is now false, which gives you the reason to exit the loop. And the algorithm has nothing after the loop, and that's why we get to post to indicate that this concludes the execution of the algorithm. So do we have any questions about this particular trace? Yes. Mm-hmm. N is 3. Yep. Okay, so the 0 on line 3 is only specifying what value do we store to whatever the left-hand side is specifying. The magic is on the left-hand side of line 3 because it is using the notation of A bracket I. Now, it is still referring to array A. Okay, line 3 always refers to array A. But what changes is which element of array A do we need to access? Because to move to the next item. Yep, yep, that is correct. Yep, that is correct. All right. Are there any questions? Yes, go ahead. Can you ask the question again? If I does not change, if I does not change, in other words, if line 4 does not exist, okay, if line 4 does not exist, then variable I remains a 0, right? So there are two consequences because of that. One is on line 3, it will keep putting a 0 on the column that is titled A bracket 0. And then the second one is because I does not change from 0 to anything else, and 0 is less than 3, so that means we cannot exit the loop because the condition that we specify on line 2 cannot become false. And since if that condition remains true all the time, we are stuck in what we call an infinite loop as a result. Okay, so do we have any other questions? Oh, go ahead. Yes, you can have two arrays. You can have any number of arrays, and the sizes of each array can be different. Yep. But we are trying to keep it simple at this point to only talk about like algorithms that only involve one array at this point. Yep. But there are no limitations as to how many arrays you can have in an algorithm. There's no limitation whatsoever. All right. So let's go ahead and take roll. Okay, so I'm gonna take roll right now. So if you have your own device, you can use your own device. And if you're on in okay, where's my mouse pointer? There we go. All right, so I am going to release the activity right now. Okay, so it is going to be below the homework assignment array 1, and it says your row on 2025-0305, which is today's date, and the access code is indexing. I'll write it on the whiteboard for just so that people can remember that. Okay, so it's indexing, which is possible only when you use an array. All right, so I'm gonna indexing. Yep, all lowercase. Right. Yes. Hmm? Yes. So you might want to focus a little bit on, when I'm talking. Hmm. And it's on the whiteboard too. So in case, I want to switch back to the module. Okay, we good? Does anyone need more time to sign in and to take roll? Nope, we're good. All right. So what we'll do now, okay, is to track an algorithm that I mentioned earlier, which is to find the maximum of the value in an array. Okay. And the algorithm that I gave you is not exactly complete. Okay. So we'll take a look at the algorithm that we just talked about, which is here. The reason why this is not complete is m needs to start with a particular value, which is not specified here. So I'm going to have to kind of work on this a little bit, okay? But the way we will do this is to use Google Drive. Okay, so I'm going to go to Google Drive, and for whatever strange reason, it wants me to sign in again, and then go to the shared folder of this class. So what this means is when we are done with this, you can also go to the shared folder from within the Canvas shell, and this spreadsheet will be visible to you. In fact, it's visible to you as soon as it is created. So right now, you will see an untitled spreadsheet, and I will change it to today's date, which is 0305. And now we can, deal with the algorithm. So what I'll do is I am going to write the algorithm in a different tool, which is mousepad. It's just a text editor, okay, like here. And let me get rid of this one. So this is the actual algorithm to find the maximum in an array of values. So I is going to start with 1, okay, so not 0, okay, so this is a little bit interesting. And m, which is supposed to track the maximum, is initialized to the value of the first item in the array. And then we say while I is less than, so how many items do you want to have in the array? 10 is a lot. Okay, that's going to take some time. 5 is probably a good. Okay, 5, 3, 4, 5 would be good. So we'll do 5. Okay, is that okay? Okay, so we'll do 5 here. And then the first thing we do inside the loop is to say, hey, if the m, which is supposed to be the maximum, if it is less than a bracket I, then we know something is not right because that means m is not the maximum up to this point. So that means we have to update m with a bracket I because a bracket I is larger than the maximum already at this point. So this is how we keep track of the maximum. But we also have to remember to add 1 to I, in each iteration, because otherwise it just doesn't move at all. Okay, so this is the algorithm. And I will give these, actual line numbers. Okay, so we say this is line 1, line 2. I could have used, just the line number, in the editor, but this is the convention that we have been using, so I'm just gonna use the same convention in this case. Line 6 is not really particularly useful, but we're gonna, give it a line number 2, just like every other line. And this is 7, and then we have line 8. There we go. All right, so now we can trace the algorithm. Okay, so we'll put this a little bit on this side and make sure that it is always displayed. All right, so now in the trace, we need the usual, starting with the line number. We have m as a variable, we have I as a variable, and instead of using m, I use 5 as a constant. Okay, do you guys want me to use n instead of 5 as a constant? I mean, it doesn't really matter all that much. If I change this to n, that means I have to make a new variable, n here, that has a value of 5 that never changes. Okay, so it doesn't really make that much of a difference, but I suppose it is more consistent with the rest of the lecture. So we'll do it this way. And then we have a bracket 0, a bracket 1, a bracket 2. Hmm? M is the maximum of the 5 values. It has to be unknown to begin with, okay, in this algorithm because of the way it is initialized later. Okay, so we'll keep these short, and line number does not need that much space either, so we'll keep it a little bit narrower too, like so. Okay, so this is the this is unknown. Everything is unknown basically, but we do need to know the 5 values in the array because otherwise, how do you find the maximum of those, right? So we're going to have to make assumptions about the 5 values in the array. So we'll go like 2, 5, and then just 1, and then the 7, and then the 6. Okay, that's just how I want to play with this particular sample program. Okay, so do we have any questions about the precondition? In other words, the values that are not question marks on row 2 of the spreadsheet, they are just assumptions for this particular demonstration. Is that okay? All right. All right. So now we run the code on line 1, I becomes a 1. Okay. On line 2, M is A bracket 0. Okay. So A bracket 0 refers to column E. It has a value of 2. So M is going to get that particular value. I'm going to use a spreadsheet feature to do this. Okay. It's the same thing as copying that value of 2 manually, but I just use the spreadsheet to refer to it. So now we get to line 3. Line 3 is asking, is I less than n? I has a value of 1 at this point, and n has a value of 5. It is a constant. 1 is less than 5 is true. So that means we go to line 4. Line 4 is a conditional statement, or the beginning thereof. Yes, it does not have to. Because if we already initialize m as a bracket 0, we know that a bracket 0 cannot be less than a bracket 0. So that means in the first iteration, the condition no, the condition of the conditional statement is guaranteed false. So it's not going to do anything. It's not going to do anything wrong either. We just don't need that iteration. Okay. All right. So moving on to line, but that was a good point. Okay. We could initialize I to 0. It just doesn't do anything particularly useful. Yep. You mean how did we get this to here? Those are just assumptions. I'm just using these as an example. So they're given to you as a precondition, which means that's just given to you. Don't ask me why. Yeah. Okay. All right. So we are now on to line 4. Line 4 has its own condition to evaluate. So I have to type it as m is less than a bracket I, and then we have to say whether it is true or not. What do you think? What is the value of m at this point? M has a value of 2. And then what is a bracket I? Okay, well, what is I anyway? I is 1, and what is a bracket I? It's a bracket 1, which has a value of 5. Okay, so now the question really is 2, which is m, less than a bracket 1, which is 5? 2 is less than 5 is it true or not? It is true. Okay, so that means we have to execute the then portion of the conditional statement on line 5, and that means m is going to be updated here to the value of a bracket I. And tell me again, what is I? I has a value of 1, so that means a bracket I refers to a bracket 1. So that means we're looking at this particular value here, and as a result, the maximum is now updated. Is that okay? All right. So after the then statement of the conditional statement, we continue on line 7 because line 6 does not do a single thing. We do not track line 6. So on line 7, I is incremented from 1 to 2, and then we go back to the beginning of the while loop, which is on line 3. So we ask the question here, I, which now has a value of 2, is it less than n, which has a value of 5? Yep, that is still true. Okay, then we go to line 4 again. And now we evaluate, is m less than a bracket I? So now we have to be careful because m is now having a value of 5. I has a value of 2. So that means a bracket I has a value of 1 because a bracket I is a bracket 2. A bracket 2 has a value of 1. So we are really asking 5 is less than 1. Is it true or false? It is false. Okay. As a result, we do not perform the then statement on line 5, and we skipped all the way to line 7. Do we have any questions about why we skipped from line 4 to line 7 in this case? Because the condition of the conditional statement is false, and there's no else statement in this case. Okay. So we skip to line 7, and line 7 is incrementing I from 2 to 3. We go back to line 3 again, and we keep asking this question, right? I is less than n. I currently has a value of 3. 3 is less than 5 it is true. And then we go to line 4, and line 4 is asking m is less than a bracket I. I now has a value of 3. So a bracket I is referring to a bracket 3. A bracket 3 is column H. It has a value of 7. M, on the other hand, has a value of 5. So the question really is asking 5 is less than 7 it is true. Very good. As a result, we have to go to line 5. Okay, so line 5 says we need to update M based on a bracket I. But since I is 3 at this point, we are updating M to the value of a bracket 3, which is 7. And then we get out of the then statement. We continue on to line 7. I is now incremented from 3 to 4, and then we go back to line 3 again to reevaluate the while condition. I is 4, n is 5, so I is less than n is true. And so we have one more iteration to perform. So I'm going to have to do this little trick here, okay, just so that we can keep certain portions of the algorithm or the table. Um, it has to stay put. Line 4 is still asking, is m less than a bracket I? M currently has a value of 7. I has a value of 4. So a bracket I is referring to a bracket 4, which has a value of 6. 7 is less than 6 is false. Very good. So this is false, which means we do not perform line 5. We skip all the way to line 7. And that's going to increment variable I from 4 to 5. We do not get to post right now, okay, because we always have to go back to the condition of the while loop first. So now we have to reevaluate the condition on line 3, which is I is less than n, but this time the answer is false. And that's when we get to post so that we can conclude the trace of the algorithm. Do we have any questions about this trace? Now you have access to this trace right now. Okay, if you go to the shared folder, which there's a link from the top of the Canvas shell. So you have access to this document already. One thing you can do with all the traces that I share with you guys is to make your own copy. Then you can also add additional annotation to the trace that I do in the class. So you can start to explain things in your own words. You identify things that are really kind of tricky, maybe to you. Okay, so that way you have your own version of the same spreadsheet. And to do that, okay, there are a few ways to do it. To make your own copy of a spreadsheet, one way is to go to File, and if you prefer to keep everything in the cloud, you can always just make a copy, and then you'll make the copy in your own Google Drive. Then you can do whatever you want with it, and it's still in the cloud. On the other hand, if you prefer to save the file to someplace on your own hard drive, you can go to Download, and you have a variety of formats to choose from. If you already have Excel installed on your computer, you can download as Excel. Okay, you can add color coding, all kinds of cool stuff to it. Open Document is the open source Office suite. PDF does not really give you a lot of option to annotate, but you can get some tools that can annotate in PDF. I cannot think of reasons why you want to save it as a HTML or CSV or TSV in this case, but there are options too. So all of these are options for you to make use of the traces that I have done in the class. So I'll do one more thing that can be helpful to you, which is to copy and paste the algorithm as a part of the spreadsheet. Because otherwise, if those two are separated, then you may not remember what the algorithm looks like. So now you have the algorithm as well as a part of the document. So are we good? Okay, so this is a resource for you guys to study. Unfortunately, when I copy and paste, the indentation is gone. So you're gonna have to go back and kind of add the indentation yourselves. Is that okay so far? Okay. The other thing I can also do, which is not very accessible, so if anyone in this class is visually impaired, this is not a good way to do it. But since I used the other approach already, I think it is okay for me to do it this way as well, is to just copy and paste an image of the algorithm into sheet one. So this way it is just super easy to get back to because I just kind of put this right here next to it. All right. Any other questions about how we use arrays? So let me just kind of ask you guys again, what is the most powerful feature of using arrays? Why is it cool? Okay, 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 okay. It is close. Okay, go ahead. Okay, but specifically, what feature allows you to do that? Okay, that's kind of the question. Okay, he had his hand first, and then I'll get back to you. Go ahead. Okay, go ahead. Okay. I think you guys all have the right idea. You just cannot verbalize your what you want to say. Okay. The most important part is the indexing mechanism. Okay. In other words, I'm referring to the use of the square bracket because you can use any expression between the brackets that evaluates to a natural number. And as a result, you can now design algorithms where it is the same line. Okay, so let me go back and kind of pull this one a little bit to the left. line 4 does not change, okay? It is the same line for every iteration of the loop. What changes is really just the value of I. But by changing the value of I for each iteration of the loop, that means every iteration is comparing a different element of A against the maximum known at that point. Okay, that is why arrays are so useful. Okay, the same line of code, by determining the expression between the square bracket, I can now have the same line to refer to different elements of the same array depending on the expression and also the variable in the expression that I put inside the square brackets. Is that okay? That really is the essence of why arrays are so useful. Hmm? Yep. It's the square brackets and inside the square bracket is just an expression that has to evaluate to a natural number. What is a natural number, by the way? I have referenced that particular term quite a few times today. What is a natural number? Yep. It's a non-negative integer or whole number, if you will. But zero is a natural number. Hmm. Yep. Yes. Yes. So you're a little bit ahead of what we have introduced so far, but I will answer that question. So if you're distinguishing between integers and floats, then the entire array have to be floats or the entire array has to be integers. Right. And that distinction is not present in a lot of scripting languages. So in JavaScript, there's no distinction between an integer versus a float. But in C++, there is. But we have not even mentioned, types, or refined how we represent numerical values to that point. But I would like to answer the question nonetheless. Hmm. All right. So, are there any questions about the algorithms that we have covered up to this point? This one finds the maximum. The earlier one that we talked about is about initialization, so I can close this one without saving. Okay. So the earlier one that we looked at is for initialization. So I'm going to go to an algorithm to find a specific value in an array. Okay, in this case, it is an unsorted array. All right, we're just looking at this term here, unsorted array. What does it mean? Hmm? You're correct. You're correct. So sorted means there's a particular order about the value of the elements in an array. So when you talk about sorting, you can say, oh, this array is sorted in a non-decreasing way. You can also, sort it in a non-increasing way. So there are two different ways to sort values in an array. Now, the reason why this algorithm is for unsorted array is because there are far more efficient ways when we have to deal with an array that is sorted. Okay, so we'll talk about binary search when we get to that point, which is a very efficient algorithm to find a specific value in an array that is sorted. Okay, but just to give you a preview of the efficiency of that particular algorithm, I will ask you a question, okay? So let's just say that, like, I write it on the whiteboard. So let's just say that, for an array of, I don't know, 63 items, it takes me about 2 seconds, okay, to find a specific value or whether the value exists or not within an array of 63 items, okay? That's just an assumption, okay? It's an assumption. So let me ask you, how long do you think it's going to take to find um, a specific value in an array that has 127 items, just on the average? Hmm? It is not. Okay. So this may not give you enough information, okay? It is not 3 seconds, it is not 4 seconds, it is a lot less than that. It's a lot less than that. Okay. So the way this works is the amount of time it takes to search for an item in the binary search, not the algorithm that we are going to talk about here, but another algorithm is a more advanced algorithm, is it is proportional to the log of the value. Okay. So do you still remember log in math? Okay. All right. So what this means is the log of 63 divided by the log of 127 is going to be the same as 2 seconds divided by whatever this amount is. I will call it x. Okay. Somebody is going to complain and say, but Jack, there are different logs. Okay. There's natural log, log of 2, log of 10, and so on. Well, they don't matter anymore. Okay. Because if you divide a log by another log, but they have the same base, the what the base of the log is does not matter anymore. Okay. So now let's go ahead and do some calculations. So I'll do some calculations here using the spreadsheet that we just created a little bit earlier, and we'll just add a new tab here. Okay. So how do we solve for this x? Yep. So we basically just move x over here and then flip this one over here. So now we are looking at x equals to 2 times the log of 127 divided by the log of 63. Does that make sense? That's algebra. Okay, cool. So we'll just go ahead and type that in. We're looking at 2 times the log, okay, log log, and it doesn't even matter what base we're dealing with here. So the log of 127 divided by the log of 63 is 2.38 seconds. Did you expect that? 2.38 seconds. Okay. Yeah, go ahead. hmm I just made an assumption of 2 seconds because you have an array of 63 values, right? But they are sorted. I have a specific value. I want to see if it is even in the array or not. That's kind of the problem. I just need to know whether a particular value is in the array or not. So what about 255 items? What do you think it's going to take to find out whether a particular value is within 255 items of an array? Yep. And approximately, can you give me an estimate? Just based on these two values, can you give me an estimate of how long it's going to take to confirm whether a value is within an array of 250? Sorry, 2 point. Yeah, 2 point. So it'll be twice this, which is what, 7.6 ish. Yep. But you can see how the amount of time scales really well with the size of the problem because we double the number of items in the array, but we're only adding a fraction of a second to how long it takes to confirm whether a value is in the array or not. So let's push this a little bit, okay? And this time I'm going to need a calculator. Let's say we're talking about the population, the entire population on Earth, which we'll just say is about 8 billion, okay? So how long would it take to confirm whether a particular item is in an array of 8 billion elements? Okay, so I can give you an estimate, okay? How many times do you have to double until you get to 8 billion from say 255? Okay, so let me phrase the question again because I think it is important for you guys to understand how to work this math out in your head. okay, in your head. So 8 billion, how do we write 8 billion? Okay, two, three, one, two, three. That's 8 billion, okay? So we look at this number and go like, oh, okay, to find the log of this, it's not going to be something that I want to do by hand. But I can do something like this. This is approximately 1024. Okay, 1000 is about 1024. This is another 1024. This is another 1024. Why 1024? Because 1024 is 2 to the power of 10. Okay, so this is 2 to the power of 10. This is 2 to the power of 10. This is 2 to the power of 10. This is 2 to the power of 3. So that means a billion is approximately 2 to the power of 33. Does that make sense? Okay. What about 255? Approximately as a power of 2, which one is closest to it? 2 to the power of 8. Okay. So 255 is approximately 2 to the power of 8. So the question is, how many times do we have to double until we get to 8 billion from 255? You just do a subtraction. 33 minus 8 is no, 25. 25. Okay. So we are now looking at approximately 25 times 0.38. This would be the addition of time on top of 2.76 seconds to confirm whether a value is within 8 billion or not. Now, it's just a ballpark number, okay? The exact number, we can just do the calculation here, and we just replace this with 8 billion, okay? 8, 1, 2, 3, 1, 2, 3, 1, 2, 3. It's only 11 seconds. That doesn't sound too bad, right? And that's why, this is what I mean by scaling up. Remember, we talked about scale up, earlier today. The binary search algorithm scales up really, really well, okay? Because every time you double the number of items in the array, in this example, it's only adding 0.38 of a second to handle an array that is twice as large. Okay, so we'll talk about the binary search algorithm for sure later in this class, but I just want to introduce the concept of what scaling up means in the context of this class. So there's the complexity of the algorithm, and then there's also how much time it consumes in order to solve a problem given a certain size. All right. So you do have a new homework assignment. I want to make that clear. I don't want anyone to miss that. So your new homework assignment is array 1 because there will be more array homework assignments. This is array 1. You have 1 week to work on it. This is your homework assignment. It's due on the 12th of March. So next Monday we can potentially talk about the homework assignment, or you can use my office hour, okay? Or email me. So I'll see you guys next Monday. Have a nice weekend. And hopefully I can talk about the exam also next Monday.